Hi everybody, welcome back to the bench. I'm almost done. I have all the footage just about shot for the next part of our Fisher X101C video. When I get a chance, I'm going to try to get started on editing it. I'm still waiting on a couple of parts that may be in the next day or so. So we're getting really close on that. In the meantime, if you recall, the last video I just posted had to do with tube talk, and what I was talking about was the difference between a beam tetrode or beam pentode, however you want to word it, and an actual pentode that actually has, instead of the beam formers, if you recall the little beam formers here, to have an actual grid. And actually, the comments on that video kind of got a little bit off of that because I really didn't get into great detail about the filament and so forth and the cathode portion. And then it brought up different comments when I did that tube dissection about that the internal parts of the tube, namely the cathode, is radioactive and may be very dangerous. And, as you noticed in the video, I was wearing gloves, which I typically do when I disassemble anything like that, just because of all the chemicals and things that are involved inside the tubes. There's parts of the tubes that are just metal, but there's other parts that are coated in different types of materials. And some of you brought up the fact that tubes can be, as we call, radioactive. Now, as the internet would have, a lot of things go around in the rumor mill, and a lot of times there can be misunderstanding about what it is. So I'm going to try to address that a little bit in this little video, and then show you a couple of examples. So one of the things I wanted to do was actually bring in my radiation survey meter. I do have 1 meter left from the old days. It's not a Geiger counter that can measure down into the range that we would have to see, and I could not for the life of me find it. One of my employees may have it somewhere, in his car or at home or something. So unfortunately I couldn't do a live demo with that, although I don't have too much to demo on, because what you're going to find out is that well, we'll see. Anyway, if that sounds interesting to you, stay tuned. That's what this little video is about. So first, let me preface this video by saying all radiation is dangerous. Okay? Get that straight right now. All exposure to ionizing radiation, and even some non-ionizing radiation, is dangerous to your health, especially if you come in contact with it. Now, how you come in contact with it and so forth will determine the risks of that danger and how dangerous it is and so forth. And that can be a big, long video that I'm not going to get into in this. So do not take away from what I'm going to say. Don't take away that any exposure or touching or coming in contact with anything radioactive is safe. It is not. 100% not. Okay? But hopefully I'll kind of give you a better understanding. So that's my little disclaimer here on this video. So the comments came from when I took one of these, which is a 7591 audio vacuum tube, and I broke it down into its individual parts to kind of show what some of the components look like and how you can tell a beam tetrode or a beam power tube versus an actual pentode, which would, instead of this beam forming device, would actually have another grid positioned over the screen grid, and they're all aligned and so forth. We got into that a little bit. And the comment came up that, I was putting myself in danger because I opened this tube up, and the tube contains an element called thorium. Now, thorium is a mildly radioactive metal. And the reason that it's used in tubes when they use it, it's used in a lot of things, by the way, it has some interesting properties. First of all, thorium has a very high melting point. So just like tungsten, it takes a lot of heat to melt it. But even better than that, it is a very good conductor of heat. And because of its composition, it lends itself well to releasing those electrons. It helps create that electron cloud for the space charge when you heat it up. So the first thing we need to understand is, how is thorium implemented in a tube itself? If I slip and say X-ray tube, it's because I teach X-ray classes sometimes, and so I get in that mode. So vacuum tubes, okay? So thorium is not like a paint. I know I've heard comments where people say that the thorium is actually a paint that will rub off and get on your hands. And that's not really the way that these are made. Tubes that contain thorium in the cathode have what's called a thoriated filament. And the process of making a thoriated filament is, you take the tungsten, and the tungsten is the base metal that you make your filament out of, and you sinter it with a powder composed of thorium and possibly some other compounds. Sinter it at high temperature, and then it's cooled and it's drawn into a wire. I'm kind of reluctant to call it an alloy as per se, but that's kind of what it is. It's an alloy. It's a metal. It's one solid piece, and it contains thorium. And the thorium does somewhat off gas, if you want to call it that. It does come out of the tungsten during the process of, well, if it's in air, it can, it can release itself, and also in the presence of heat and electrons, it can definitely escape from that. So a lot of times what they'll do is they will coat the filament with like a ceramic type of coating, or an oxide coating that can contain any number of compounds. And that's the purpose of that, is to kind of keep that from depleting too quickly. So it makes the filament last longer. But that in and of itself is not a radioactive element. It usually contains ceramic, and it can contain, I think, boron. Some of them can contain aluminum oxides. Some of them can contain a barium oxide, I think, or something like that. Again, I'm not a chemist, but just so you understand what that is. So what does this all mean? Well, first of all, you're probably not going to get anything, at least from this tube, on you if you accidentally come in contact with it. Second of all, this filament here, this is the filament of the 7591 right here. And you can see it's just a spiral wind of wire. And it may or may not be thoriated metal. A lot of them were not in these types of tubes, but they can be. That is what's in here. Now, the thing is, this actually slips up inside this little tube here. And this little hollow tube is actually the cathode. And that's one thing I didn't get into, is a directly heated tube versus an indirectly heated tube. In a direct heated tube, the filament acts also as the cathode. So not only would you put your filament current through the filament, but you would attach the negative side of your tube voltage between anode cathode to one leg of your filament, and the filament becomes part of the actual circuit. In this case, the filament actually just acts like a heater. So as this filament heats up inside this little metal tube here, it heats this tube up. And if you look very carefully down here, see there's a little wire on there? That wire is actually the connection to your cathode. So this is where you connect your negative or your ground or whatever, your cathode connection. That would go to the cathode pin of your tube. And this white coating that you see out here is not thorium. It's actually an oxide coating that contains ceramic, and like I said, some of those other elements that we're talking about, like I said, it can be an aluminum oxide. It can have with ceramic. It can also be barium oxide, I think. But anyway, the purpose of this is twofold. Number one, the ceramic also helps conduct the heat and spread it evenly along this metal tube. It also acts, more importantly, as an insulator. If you recall, this is positioned inside this, which is your control grid. This is the grid, the control grid. And if you notice, this is very, very close to this. When it's inside there, these little wires are almost touching here. So this actually acts as an insulator in addition to a heat spreader. And the actual electron cloud is formed by the heat that this produces. And that heat is driven by this filament. So the thorium isn't as big of an issue in these. And even if there is thorium in the filament, it's very low. It's centered into the metal. And if I had my survey meter, I don't even know if my meter will go low enough. You almost need a Geiger counter, which we never used those. Back in the day when we used to service nuclear gamma cameras and things, we would use that to check for residual activity of some of the isotopes we worked with. But again, every hospital had their own Geiger counter, and we used it. It was calibrated and so forth on site. So we just used that. So we really never had a need to have those. And all of the other radiation test gear that we use today is for gamma radiation, much higher energy. Another thing about thorium is it emits alpha radiation, which is very low-level radiation. And that level, let me preface this by saying, any radiation is dangerous. Okay, there's no doubt about it. So if we did have a Geiger counter handy, I think what you would find is that the activity of this would be extremely low, and then you would have to get the probe pretty close to it if there was thorium, if it was thoriated tungsten. You'd have to get pretty close to pick something up. Alpha particles, which is what thorium releases, does not have the ability to penetrate anything very much. It can't penetrate very deep. As a matter of fact, it cannot get through your skin. It can get on your skin. It cannot pass through for instance, the anode. It can't pass through that. It cannot pass through the glass envelope of the tube itself. So this glass here would block it. And really, the main danger to that type of in the very, very small quantities like this, the main danger to that is if you get it into your system. So I certainly wouldn't want to breathe it in. I wouldn't want to touch it and get it on my skin and then rub my eye. I wouldn't want to eat it. I wouldn't want to use it as a suppository. Definitely, you don't want it in your body in any way, shape, or form. Once it gets into your bloodstream, it can collect in certain organs, and those alpha particles will cause damage to you and do run a risk of causing cancer. So those of you who did say that you need to be cautious, you were 100% correct. And especially when you don't know about these things, treat every X-ray, or there I go, X-ray tube, I told you. Treat every vacuum tube as if it has radioactive material in it, even if it doesn't. That way, you will always be practicing safe procedures when handling these things. In the first place, there's no reason to take this apart. I've already done it for you, and you can see what's inside here. When you do see these open, like if you drop a tube and it breaks, don't pick it up with your bare hands. First of all, you have glass, you'll cut yourself. But second of all, wear gloves. Wear disposable gloves. If there is some sort of a material in there that's hazardous, even if it's not radioactive, what if it's just a chemical that's toxic? You don't want to come in contact with that. So use gloves, dispose of it properly. And if it is absolute biohazard, then make sure you dispose of it according to your, the laws of your area that you live and so forth. This stuff's serious, But in this case, this did not present a big danger to me. I was not hurt by it, and I did not expose myself to radiation. Also, when you deal with radiation, you have the inverse square law working for you. And what that means, and without getting into great details and so forth, as you increase the distance from a point source of radiation to yourself, every time you increase that distance, the amount of radiation you're exposed to will decrease till it decreases to almost a negligible or unmeasurable amount. And basically, when you double the distance between you and an object, you reduce the activity that you're exposed to by a factor of 4. So it really, you don't have to get too far away from a source like this to where you're receiving no dangerous exposure level at all. That being said, you don't know what the activity level is. So again, don't go around it unless you understand, unless you know. Okay, so if this really doesn't have much or any thorium at all, what does? Let's talk about that. Okay, so here's a great big tube. And just for some comparison, here's my hand. And what this is actually a tetrode. So we were talking about tetrodes not being very common. Well, I lied a little bit. In my industry, these are still common, although they're getting outdated. There's solid state equipment out there that can take the place of this. It's much smaller, more efficient, so forth. But this is actually a tetrode tube, and it is a vacuum tube, believe it or not. So you have your anode, and then you have your filament up here. You have your control grid, which actually is 2 pins on this one, and then you have your cathode. And this tube is actually, I'm sorry, your filament is this is a direct heated tube, directly heated. It is not indirectly heated. So the filament is in fact the cathode. So you have your 2 filament windings, or 2 filament pins. You have 2, I believe, control grid pins, and then you have a screen grid. And believe it or not, the control grid is biased at about we put about negative 4,000 volts, or negative 4 kV, minus 4 kV, to bias this thing. That's just on the grid. The tube, this particular one, this is a 5186. This one can handle up to, I believe, 80 kilovolts, 80,000 volts between the anode and cathode. And the purpose of this tube is to switch very high energy electricity in the range of up to 75 kilovolts in the circuit that it's used, and in excess of 1 amp at that power. And it can switch it very rapidly, up to 90 times per second, on and off. And it's used in a special type of X-ray equipment. And this does use a thoriated filament, a very large one. And there is a pretty good amount of thorium in this. As you notice, I'm not afraid to touch it. I'm right next to it. But the filament itself is located way down inside this cup. So you see the anode cup up here, and it's kind of a spun brass or copper. And the filament is inside that copper envelope in the anode. And then this is very thick glass. So the bottom line is, and you can see the splatter up in the top here. You see it? This thing had a little accident. That's why it's now just a paperweight. But this does have a thoriated filament. And again, because of the metal, because of the glass envelope, thorium is low activity, alpha radiation. That alpha radiation cannot penetrate this. So there is absolutely no danger in being radiated by this tube. Now, if I were to break it open and remove the filament would have a little bit of radioactivity to it. And if I did get too close to it, I could be exposed to a very small amount of radiation. Now, for a short duration, it won't kill you, but any exposure, as I said at the beginning of this video, any exposure to ionizing radiation does have a small, even if it's infinitesimally small, there will be a probability that a cell could be damaged and mutate into cancer. Always remember that. So that is why you would never want to come in contact with it, especially in a large quantity as this thing would have in it. So again, if it's all together in one piece, yes, there is radioactive material in it, by definition, but no, this is not radioactive in that it's not coming out where you can be exposed to it, as long as it's all together. Hope that helps. Now, you might ask yourself, well, are there any devices that we will see in the audio field, with audio tubes, or ham radio, like a ham radio transmitter? And the answer to that is yes. So here's a rather large example of something that would have a thoriated filament, and it is a type 845. This is an original RCA, and it's a type 845. These were originally designed as like a radio transmitter tube. This actually came out of an old, I believe it was an RCA Voice of the Theater amplifier out of a movie theater in my hometown where I grew up originally. And they were remodeling the theater, and they had the amplifier crammed away in an old closet. The thing weighed like 300 pounds. And it used 2 of these on the output, and it used 2 of the type 866 rectifiers, which that's another subject. They have mercury in them, and they're a lot more dangerous than this, if you ask me. Way more dangerous if you open them up. I would never open one of those up. But these are quite often used in single-ended amplifiers, because and that's what this was used in, because of their sound quality. They're a fantastic sounding tube, especially these originals. This, I don't know what this thing's worth. I bet it's worth a lot. But anyway, this, if we look at the data sheet, let's take a look at it. The very first thing it says at the very top, thoriated tungsten filament. And actually, there are audio people out there, audiophiles, who actually favor the thoriated tungsten filament because they believe that they do a better job of creating the electron cloud, and it creates for a better performing tube that sounds better. Again, I'm not having an opinion on that. I'm just saying there is a following for that, and they're very popular for that reason. So I'll show you what it looks like. This is called a direct heated tube. In other words, it does not have a cathode element in it. And if I have it connected to some jumper leads, and if we put some voltage, I won't run this up to full voltage for the filament, because the filament can run at 10 volts. But you can see, if you look down in there, you can see the filament. You can directly see the filament in the tube as it's lit up. And that's because this is a direct heated tube. So you can see the 2 wires. And that's what we mean by that. And that is a thoriated tungsten filament. And just by running the filament, that thorium is actually being released from that tungsten. So it will deplete. It does have a life expectancy, and it will deplete over time. And as it depletes, the tube becomes less efficient. And as it becomes less efficient, you have to increase the filament voltage if you have the means to do that. And it'll last you a little bit longer, but eventually it will fail, and the tube will lose its emissions. And the thorium actually helps the tube be more efficient at creating the electron cloud, and as opposed to plain old tungsten. X-ray tubes as well, they use thoriated filaments. And again, with things like X-ray tubes and like this tube, they actually will vary the filament voltage sometimes. And in an X-ray machine, the filament has to be adjusted very quickly, and the temperature of the filament has to react very rapidly, because in an X-ray machine, you actually have to make the change of filament current and voltage and so forth. It has to be able to react within about 1 millisecond. And because of that, you could never use an indirectly heated cathode. So to have, one of the drawbacks of using this is the filament has to heat this up, and you have to wait for this to catch up to the temperature of the filament before you get the stabilized results. Whereas, you know, and that's an advantage on an audio tube, because think about it, if there's noise or if there's ripple on that filament here, you're not going to see that, because this thing's not going to change temperature that rapidly. It's just going to take the average temperature of that filament and stabilize to that. The downside is you can't change it. It's not as rapid of a change when you change the filament voltage. But of course, in an amplifier or a radio or a transmitter, the filament voltage is fixed. It never moves, so it's not an issue. So just giving you a little bit of idea of how this all works. Now, before I close this video, the last thing I want to do is give you a couple of ideas of a few other things that you need to be aware of in the industry that are not vacuum tube related. So for instance, if any of you have a gas camping light, you know, like the propane lanterns that have the little mantles in them, the little white looking tubular wick that they use. Do you ever notice how bright and white those things burn? It's because they are impregnated with thorium. And they have a lot more thorium than your little filament in your tube is going to have. And they're pretty radioactive. If you actually measure the activity with a Geiger counter of a freshly made one, you would be surprised how much activity there is there. Welding rods. There's a lot of welding rods out there that use thorium. Again, thorium is a very good conductor of heat, and it's a fairly good conductor of electricity. That's another reason that you would not coat the outside of this with thorium, because thorium is conductive. And if you're going to put it inside this little what's it called? Grid. I'm sorry. If you're going to put it inside this little grid here, obviously you don't want it to short out if it touches, you know. So this ceramic actually acts as a little bit of an insulator. So welding rods, because of their conductance and because of, again, the way that the thorium reacts to the heat. So believe it or not, whenever you're picking up those welding rods, you're touching a thoriated metal. How about that? I bet some of you didn't know that. Now, the other thing you have to watch out for is mercury. So those mercury rectifiers we talked about, like that type 866, compact fluorescent CFL lights, you know, and fluorescent light bulbs, they have a little bit of mercury inside of them. Mercury is a toxic chemical. It's not good, and you do not want that on your skin. It'll soak through your skin. That's worse than the thorium. Another thing you have to watch is radium. The old glow-in-the-dark clocks. They used a phosphorescent paint to glow in the dark, but the thing that drove that phosphor to glow, to scintillate, is radium. And radium's nasty stuff too. Radium has a shorter half-life than thorium. Thorium has a really long half-life. In other words, it has a half-life that's longer than the age of the Earth. So the bottom line is, in none of our times are we ever going to see thorium change in activity, because of the half-life is so long on it. Whereas on the radium, it does have some half-life. It'll die down, which is why the old glow-in-the-dark clocks don't glow as well anymore, or at all. Not only does the phosphor lose its ability to scintillate, but the radium will actually lose its energy. So anyway, just a few things to know, and I hope that clears up the water with that. But always be careful around anything that you're not familiar with. I'm not going to say just be cautious around things that are radioactive. Be cautious around even things that you don't know if it has toxic chemicals or radioactivity. Always be careful. But I thank you all for bringing that up, and especially those who posted those comments about that warning, because it's very important. And probably I was pushing through that video and it was getting long as it was, but I really should have taken the time to explain that a little more, so I appreciate you all reminding me. And as always, I wish you all peace, joy, happiness, and good health in your lives. Thank you for all the wonderful comments. And if you like these little tube talk videos, or talk videos about any kind of thing like that, let me know down in the comments. And maybe we'll do a couple more of them. All right, take care, and we'll see you next time. Bye-bye.